Mr. Sutton here, bringing you the AB Calculus 2-4 Part 2 homework solutions on limits of absolute value and the squeeze theorem. On this problem, I'm trying to find the limit as x approaches 2 from the left side of 2x minus 4 over the absolute value of x minus 2. So to start this problem, first thing I'm going to do is I'm going to give this thing that I'm taking the limit of a name. I'm going to call this 2x bit here. All of that, I'm going to call it f of x, so I can easily refer to it. And I'm going to rewrite this as an absolute value, or a piecewise function, because absolute value really is just a piecewise function. So this piecewise function is going to have two rules. One rule for values of x that would make absolute value, the stuff inside, come out negative, and another rule for values of x that would make the stuff come out positive, because absolute value behaves differently based on negatives versus positives. So x equals 2 is the turnaround spot where I stop getting negative results and start getting positive results inside when I plug in x values. So I'll have one rule for x less than 2 and another rule for x greater than 2. Now if x is less than 2, the stuff inside is coming out negative, so to simulate absolute value, I need to negate all of the stuff in there. And I'll do that by doing a negative parentheses x minus 2. This way, whatever this negativity is, it's just going to be made positive. Now, if x is greater than 2, the stuff inside here is coming out positive anyway, so I don't need anything special to do that. I'm just going to lose the absolute value in that case. Before I can actually evaluate the limit at 2, you'll notice if you plug 2 into either of these rules, you're going to get 0 over 0. So we need to first factor and cancel out some things. 2x minus 4, I can factor a 2 out of those. That'll leave me with a 2 parentheses x minus 2 for both of those rules. And then in each of these rules, I can cancel out the x minus 2's, leaving me with negative 2 and positive 2. So those are my simplified rules. Now for the left side limit, I have to use the left side rule, the rule with stuff that has x less than 2. So that's going to come out to negative 2. We're just using that first rule. To find the limit as x approaches negative 1 of this absolute value fraction hybrid, we're going to rewrite this as a piecewise function. So first let me name this thing. I'm going to call this f of x just so I can easily refer to it. And now I'm going to split this up into a piecewise function. I'm going to have two rules, one that makes the stuff inside the absolute value negative, one that makes it positive. So the rules are going to switch around when x is negative 1, because that's the place where this absolute value stuff takes on a value of 0. So I'm going to have a rule for x less than negative 1 and a rule for x greater than negative 1. For less than negative 1, to make the stuff inside here that's originally negative come out to a positive, I'm going to have to write negative parentheses x plus 1. That will simulate the make it positive thing of absolute value. For the other rule, if x is already going to be greater than negative 1 and the stuff inside here is coming out positive, I don't need anything special. I'll just get rid of the absolute value and write x plus 1. All right, now in order to evaluate this at negative 1, if I plug that in right away, I'm just going to get 0 over 0 in both of these situations. So I'm going to first factor a 4 out of the numerator in each of these rules. That'll leave me with an x plus 1. The benefit of doing that is that I can now cancel out the x plus 1's to get rid of that problem. So I'll end up with reduced rules of negative 4 and positive 4. And now for the two-sided limit, since this is a border value, negative 1, I actually have to plug negative 1 into both sides. So for my left side limit, I've just got this constant of negative 4. For the right side limit, I've got the constant of positive 4. Since those don't match, that means that my two-sided limit does not exist. On this problem, I'm trying to find the limit as x approaches 3 from the left side of this expression. With absolute value, the best course of action is usually to split this into a piecewise function. So I'm going to give this thing a name. I'll call it f of x, and we'll split it up here. I'm going to have one rule for things that make the stuff inside absolute value come out negative, one rule that makes them come out positive. They stop being negative and start being positive if I plug in x values that are less than 3 or greater than 3. So less than 3, I get negative stuff inside. Greater than 3 will give me positive stuff. So for the less than 3 rule, the negative stuff rule, I'm going to simulate absolute value by negating x minus 3. So I'll write this as a negative parentheses x minus 3. And then for the rule for where these come out positive, I can just lose the absolute value in that situation. Now I can reduce this a little bit. This will be a -1 for the first rule and +1 for the second rule. So that's worth doing so that I can take the limit. Now for limits, they said they wanted 3 from the left side. The left side limit means I have to use this first rule only. So that's just going to be -1, which is going to give us answer choice B. To find the limit as x approaches -7 of this absolute value expression, I'm going to first give it a name. I'll call it f of x. But after I do that, I'm going to split it into a piecewise function. So my two rules for the piecewise function, I'm going to have one rule for x values that make the stuff inside here negative. So those would be all x values that are less than -7. And then I'll have a rule for all the x values that make this positive. So that's going to be all the x values that are greater than -7. So for my less than -7 rule, to make stuff come out positive, I'm going to negate everything in here. So negative x plus 7 in a parentheses is how I'm going to rewrite that absolute value denominator. And for things that make the stuff inside positive, I'm just going to lose the absolute value because it doesn't really need to do anything special if things are already coming out positive. So reducing these, I can rewrite these two rules as -1 and +1. And now for the two-sided limit as x approaches -7, since -7 is a border value and I want the two-sided limit, I need to find the left and the right side limit. The left side limit is just this left rule here, this top rule, which is just a constant of -1. The right side limit is this bottom rule, which is also a constant, but it's a constant of +1. Since negative and +1 are not the same number, that means our limits don't agree, so our two-sided limit is actually going to not exist. So that's going to be choice D. For this problem, they're giving us a g and an h function, both of which are quadratic polynomials. And then they're telling us that f is a function that's basically sandwiched between g and h. And they want to know, based off of this, what is the limit as x approaches -1 of this f function. Now they didn't tell us what f is doing algebraically, but since it's between g and h, we can try using the squeeze theorem on this. Now in order to make this work, we have to find the limit as x approaches -1 of both the g and the h function. If those limits are the same, then that will be what the f of x limit also is. If the limits are different, then we're kind of out of luck. So let's do the limit as x approaches -1 of g of x first. So I'm going to have to crunch those numbers without a calculator, plugging -1 into this g function up here. So that's going to be -1 plus 2, which is +1, plus another 3 gives us 4. Now let me find the limit as x approaches -1 of h. So plugging -1 into this h function up here. -1 squared is just 1, so this is just 1/2. 1/2 minus 1 is -1/2. -1/2 plus 13/2 is 12/2, which we can reduce to 6. Since the two limits do not match each other, 4 and 6 are not the same number, that means that we cannot use the squeeze theorem. We cannot actually determine what the limit of f is based off of that. So that's going to lead us to choose answer choice D. For this problem, g and h are defined. G is going to be this weird sine function, and h is going to be this cubic polynomial. They're telling us that f is a function that is between g and h on the interval from -2 to 0. And based off of this, they want to know the value of the limit of x approaching -1 of f of x. Now, we don't know what f of x does algebraically, but we do know that it's between g and h. And since that's happening on the interval from -2 to 0, we know that -1, for the value of -1, f is going to be somewhere between g and h. So what we can do here is use our squeeze theorem, take the limits as x approaches -1 of g and h, and if those just so happen to be the same number, we will know that f also has to share that limit. So let me find the limit of g first. That's plugging -1 into this sine function here. So we have sine of pi over 2, -1 plus 2, all of that plus 3. So this is, let's see here, this is really just 1 times pi over 2. So this is sine of pi over 2. Sine of pi over 2 is going to be 1. And then 1 plus 3 is going to be 4. So that all comes out to 4. Next, let's take the limit as x approaches -1 of the h function. And this one's going to be a little bit more tedious. So we're plugging -1 in for all those x's there. We've got a little bit of crunching to do. We'll do it in a few stages since we can't use a calculator on this. So first, let's do the exponents. We've got -1 to the third, which is -1, times -1/4 is +1/4. Next up, -1 squared is just 1, so we don't need to worry about that. So this is just -3/2. Then this will be +9/4 and then a +3. Now to add these together, let me just get a common denominator. I'm going to make that common denominator 4. So 1/4 is fine. -3/2, I'm going to double the numerator and denominator to get 6/4. And 3, I'm going to call, let me see, I have to call that 12 over 4. There we go. So adding all this up, we've got 1 minus 6, so -5. -5 plus 9 is 4. 4 plus 12 is 16. And this is 16 over that common denominator of 4. So that all reduces at long last to 4. Tedious, but we had to be sure. Since these limits match, that means that the limit as x approaches, I should say -1 there. The limit as x approaches -1 of f of x is also going to be 4. So that's choice C. On this one, we are given a g and an h function, and we are told that f is between g and h for all x's. Based off of this, we want to know the limit as x approaches 1 of f of x. We don't know what f of x is algebraically, but we know that for all x's, it's sandwiched between g and h. So if we take the limit as x approaches 1 of both g and h, and that happens to be the same number, then we know that f, which is always between those two, will have to share that limit. If it's not the same number, then we won't be able to tell much of anything, but we have to try. So let's find the limit first as x approaches 1 of the g function. Got to start somewhere. So -2 times 1 squared plus 4 times 1 plus 1. This is -2 plus 4, which is 2, plus another 1 is 3. And that's one of the answer choices, but before we pick that, we need to find the limit as limit of h as x approaches 1. So that's going to be 1/2 times 1 squared minus 1 plus 11 over 2. We have 1/2 minus 1, which is -1/2. -1/2 plus 11 is 10 over 2, which we can reduce to 5. Now those are different. Since these limits don't match up, that means we can't really tell anything about the limit of f of x at that spot, other than the fact that it's got to be somewhere between 3 and 5. But we can't pick a specific value. Because we can't pick a single value, we would say that limit does not exist, or at least, it might exist, but we can't determine it. So that means we're going to have to pick D. And just to really emphasize, we're not saying the limit of f doesn't exist, just that we can't find it with the information that they gave us here. On this problem, they're giving us 3 functions, f, g, and h. Those are these crazy trigonometric algebraic sort of hybrid functions here. And these are all true for x not equaling 0. And they're also telling us that the 3 inequalities given in these Roman numerals are also true on the interval from -1 to 1 for all values of x not equal to 0. So in these inequalities, just to look closely at these, we've got each of our 3 functions sandwiched between 2 other functions. So now, based off of this, they want to know which of these inequalities could be used with the squeeze theorem, so you have to know what that is, to find the limit of each of the functions as x approaches 0. So the squeeze theorem says that if you have a function that is sandwiched between 2 other functions, and the limit as x approaches a certain number of the 2 bounding functions, if that's the same number, then you can conclude this middle sandwiched function also has that limit. Now, we have to make sure that the value of x that we're approaching is actually on the interval for which these inequalities is true. And they said the interval is -1 to 1, and we're approaching 0, which is between -1 and 1, so that checks out. We need to make sure the inequalities are all true, and they said that the inequalities are true. This order of things is correct. So the only other thing we actually have to check is we need to make sure that the limit of the left and the right part of these inequalities is the same number. If it's the same number, then the function inside will share that limit and the squeeze theorem will work. If it's different limits, then the squeeze theorem will not be able to help us out finding the limit of the inner function. So let's start with Roman numeral 1. We're going to find the limit of 1/4 and of x squared plus 1/2 as x approaches 0. So those two limits. The limit of 1/4 is always just going to be 1/4. It's a constant. For x squared plus 1/2, we just plug in x equals 0. So that just comes out to 1/2. Now 1/4 and 1/2 are different limits. So the squeeze theorem would not be able to help us out for Roman numeral 1. Won't help us find the f function. Now for Roman numeral 2, we're taking limits of -x to the 4th and x to the 4th as x approaches 0. Plugging 0 into both of these will result in a value of 0. So we get 0 equals 0. Since those limits match up, this is a yes. The squeeze theorem will help us here. And in fact, we could say actually that the limit of g of x as x approaches 0 is also 0. Now for the third inequality, we're taking the limit of -1 over x squared and 1 over x squared as x approaches 0. In the first case, as this gets smaller and smaller and smaller, this fraction gets larger and larger and larger. Since there's a negative out in front, that's growing to -infinity. And we have the same kind of thing happening on the right side, but we have a positive infinity instead because there's no negative out in front. Negative infinity and positive infinity don't match up, and even if they were both the same infinity, infinity is not really a number. You need the limit that you get to actually be a specific constant, not a direction. So this is also a situation where the sandwich or the squeeze theorem will not help us. So this is another no. So then out of all these, only inequality number 2, Roman numeral 2, was matching the condition that they had here. So we're going to pick choice B, 2 only.